Hello everyone, welcome back to my Chem Corner. So in today's video we're going to solve more Intext questions from the chapter Solid State for class 12. So before we move into the video, please hit the subscribe button and the bell icon so you receive notifications as and when I upload the video. So without further ado, let's move into the video. So the next question is 1.11. It says distinguish between hexagonal and monoclinic unit cell, and the second question is face-centered and end-centered unit cell. So in this, we will look at the diagram of each of this to understand what it is. So the first question is distinguish between hexagonal and monoclinic. So this is a diagram of a hexagonal. You can see that there are different edge length and there are different angles also. So let's look into it in detail. So here, when you look at it, when you have these angles which are here, the edge length which is here, this is A, B and this is C. So A and B, both the edge lengths are the same, but these are not equal to C because C edge length is the longest. So they are not the same. Now similarly, when you look at the bond length, here you have alpha and you have beta. Both of these are 90 degree, but when you look at gamma here, which is a longer, bigger angle, gamma is 120 degree. Now when you try to compare this structure with the monoclinic unit cell, they're very different. Now under monoclinic unit cell, if you clearly see, you will know all the edge length are different because you can see three different edge length here. This is A, this is B, and the one going vertically up is very longer than the other one. So A is not equal to B, which is further not equal to C. What about their angles? Here alpha and beta, both of these are not equal to each other, but alpha and gamma are not equal to each other. This is alpha and gamma are not equal to each other, but your alpha and beta here, both of them are 90 degree upward, right? So here, if you see the difference between them, they're way different when compared to each other. Hexagonal has a different bond angle and edge length. Monoclinic has a different bond angle and a edge length. Now the second question is face-centered and end-centered. So look at the diagram. Now face-centered meaning what? If you're sitting in a room and listening to this video, you can see that around you, you have four walls. One in front of you, one on your right, one on your left and one behind you. So you have four and one above and one below. So total how many surfaces do you have? 6 surfaces. On the center of each of this surface, you will find an atom in the center. Now that is a face-centered unit cell. How is it going to be different to an end-centered? End-centered diagram, if you see, if you're sitting in a room, the wall facing you and the wall behind you, those are the two ends of a crystal. Or you can say the wall that is there above you and the wall that is there below you, that is the roof and the floor. Those are the two ends of a unit cell. So you're considering any two ends when you're talking about end-centered unit cell. So both are different, they're not the same. Though we have an atom in the center of the face, for a face centered, on all the centers of the face you have one atom. But when I talk about end-centered, two ends, any two ends you can consider. Either your right and left, top and bottom, or front and back. Any two ends you consider, that is an end-centered unit cell. Alright. Now, the next one is 1.2. Here it says explain how much portion of an atom located at the center or body center of a cubic unit cell is a part of its neighboring unit cell. So here, first one, when you look at it, firstly you need to understand what is that particular atom am I going to mean about. So for this particular, the one that's marked in pink color is one unit cell. I'm going to talk about that one atom of that unit cell which is shared among other 8 unit cells. How is it 8? On top layer I have 4, bottom layer I have 4. So this particular atom is shared among all other 8 unit cells. So that way, for a simple cube, I am sharing that one atom to 8 other unit cells. So it's going to be 1/8 of a contribution per unit cell. This one atom is shared with 4 other unit cells on top and 4 other below, which means totally surrounding that particular atom. Now the second question says body-centered unit cell. So if you see body-centered unit cell, only one atom in the center is there that is belonging to that one unit cell. It is not shared with any other. So the contribution is only one contribution per unit cell. Alright. And the next one is 1.13. It says what is the two-dimensional coordination number of a molecule in a square close packing. Now I've done a detailed video about this in one of my videos in the previous ones. You can just open that and find out what do you mean by this square close packing or two-dimensional square close packing and all of that. But still I will just go through it roughly by showing you a diagram. So here if you see this arrangement, if I had only one layer here below, that means it was a one dimension. But now I'm going to have repeated layers one above the other. So this is one dimension, this is my second dimension. So this is a two-dimensional square close packing. Now in this case, I want to know what is a coordination number. So I've taken a random sphere over here that's in the center. How many atoms are touching it? I have one here, one here, one here, and one here. So total there are 4. So the coordination number of any atom in a two-dimensional square close packing is 4. You just see how many atoms are touching a particular atom in that entire arrangement. That way you're going to identify what is a coordination number. Alright. Now, this question clearly says a compound forms hexagonal close packed structure. What is the total number of voids in 0.5 mole of it, and how many of these are tetrahedral voids? So before we move into the video, into the question, you need to know how many tetrahedral voids and how many octahedral voids are generally there. So number of tetrahedral voids are 2n and number of octahedral voids are n. Now what is it n? N is nothing but number of particles. So first we'll find out what is n. So n, number of moles, we all know that n number of moles is nothing but number of particles divided by Avogadro's number. This we have all learnt it in mole concept also. Number of moles is equal to, in terms of Avogadro's number, it's going to be number of particles divided by Avogadro's number. In this case, number of moles we know, which is 0.5 mole in the question. Na is a constant. We need to find out what is n. When we substitute the values here, n is equal to 3.011 10 raised to 23 after we cross multiply them. So now that we know what is n, the question we need to find out is number of tetrahedral voids. Now number of tetrahedral voids are going to be 2n. So 2n meaning 2 into this 3.011 into 10 to the power 3. 23. Now when you do that, you get 6.022 10 to the power 23. That is the number of tetrahedral voids here. So that is the answer for which says number of tetrahedral void. There was a second question that says how many of these are tetrahedral void. We calculated. But there's one more question. What is the total number of voids in 0.5 mole? We need to know total number. So now what we will calculate here is, it says total number of voids is nothing but what is the total number of tetrahedral void plus the total number of octahedral void, which we'll find out here. So that will be equal to 9.033 10 to the power 23. Where if we get this number of octahedral void? Because number of octahedral void is n only, and we already find out. We have already found out here. So when you substitute it, you will get what is the total number of voids for 0.5 mole of the compound. Alright. Now the next question is, a compound is formed by two elements M and N. The element N forms CCP and atoms of M occupy 1/3 of tetrahedral void. What is the formula of the compound? So first thing, let's get a few information from the question. We have two elements M and N. Of that, N will occupy the CCP. CCP can also be FCC or HCP. So when you have that, we already know that the Z value or number of atoms per unit cell is nothing but 4. So that is done with N. But what about M? M is occupying 1/3 of tetrahedral void. So therefore, tetrahedral void is nothing but 2 into Z. Alright. So here, because 2 into Z is how? Because the number of tetrahedral voids are 2n. So here we can say 2 into Z, which is equal to 1/3 is occupied by tetrahedral void. So 1/3 into 2 into Z is 4. So we're writing, because it's a HCP, we're going to write it as 4 here. When we simplify this, we'll get 8 by 3. Now this 8 by 3, For the ratio, when we see 8 by 3 is by m and 4 is by n. So when we put it as ratio, it's going to be 8 by 3 is to 4. Multiply this 3 over here, you get 8 is to 12. Make them into the simple ratio, you get 2 is to 3. Therefore, the formula of the compound is M2N3. Alright, so this way it's easy for us to calculate the formula of the compound if you know how to get a few information from the question directly.